In this video, I'm going to be talking about different numeration systems, which some textbooks also refer to as different number systems. So you'll see some different terminology used. Speaking of terminology, a numeral is a word that you need to know. You can think of a numeral as a number label. So numeral ends with an L, just like label begins and ends with. So a number is an abstract idea. You can't in the wild see a 7 galloping about the fields. You can't see a 3 sunning itself on the rocks next to the lake. You can't see a 13 up in the air. You can look at examples of those. You can say, oh, look, there's 13 clouds. Oh, look, there's 7 starfish. Oh, look, there's 3 roses. But the idea of a number itself is abstract. We can't touch or taste or feel or hear or see a number. What we have instead are symbols that represent them. Those symbols are called numerals. Different cultures throughout history have devised their own systems to represent the numbers. Here we're interested in the cardinal numbers. A cardinal number answers the question, how many? So in elementary school, when we're teaching children how to count, what we're working with is cardinal numbers. How many cookies do you have? How many apples are in the bowl? How many crayons in the box? How many students in the classroom? Those are cardinal numbers. And that's a good chunk of what we use numbers for. We also use numbers ordinally. Ordinally is in order, first, second, third, fourth, etc. And we teach those too in elementary school separately from cardinal number because they're a little bit of a different concept. Here are several different historic numeration systems in not really chronological order, despite maybe what your book says. So at this top, we have the Babylonian number system. The Babylonian system used a series of wedges, and the Babylonians used these wedge shapes to represent all of their writings, called cuneiform. And so it was, as you can see, they have 1 wedge for 1, 2 for 2, and so on until they get to 10, where they have a different shape. The Egyptians, you might be familiar with Egyptian writing, hieroglyphs. Egyptian numerals are also hieroglyphs. And so we have here Egyptian numbers, or Egyptian numerals, I should say, for the numbers from 1 through 10. We have series of that looks a little bit like our number 1, doesn't it? That's the Egyptian hieroglyph for a staff, like a walking staff. And so they would put groups of those, and then when they got to 10, they chose the hieroglyph for a heel bone. Underneath that, you have the Mayan number system. And the Mayan number system, which was not done at the same time as the Egyptians, it was quite a bit after, worked with both 5s and 10s. So you see the Mayans had a series of dots instead of line segments. They have 1 dot for 1, 2 dots for 2, and so on. When they get to 5, they do something very smart. Rather than writing 5 dots, they draw a straight line. And then for 6, 7, 8, 9, they combine the dots again. And then for 10, they have 2 lines. Why do I say this is smart? This is smart because we at a glance can recognize up to about 4 or 5 objects before we have to stop and count them. And so looking here at the Egyptian stuff and the Babylonian stuff, we have to probably stop and count if we want to know the difference between 8 and 9. Or even maybe between 7 and 8. It takes us a little second or 2. The ability to automatically recognize that we have 2 things here or 3 things here or 4 things here is called the ability to subitize. Or we sometimes call this subitization or subitization. And that's being able to recognize a certain group of numbers without having to count how many there are. And I bring that up in math for elementary teachers because that's an important idea in the primary grades. There's research that shows that children who develop good subitizing skills do better in math throughout their school careers. So it's important that we not just teach rote memorization in elementary school. There's certainly a place for memorization, but that we also give students lots of practice opportunities of seeing, here are 3 balls, here are 3 jacks, here are 3 pencils, here are 4 of each, here are 5 of each, here are 6 of each. And the more we do that, the quicker students get at recognizing automatically how many are in the group. And again, that idea of subitizing, research has shown it benefits students down the road. A 6th grade teacher wouldn't think about teaching subitizing for a child unless that child had special needs in math. But in the lower grades, it's a really beneficial skill to have. So the Mayans understood this instinctively, right? They realized, hey, wait a second. And I would venture to guess that at one point in Mayan numeration, before we have examples of it that have survived, they probably did keep putting these dots and said, oh, we have 5 dots for 5 and 6 for 6 and 7 for 7. And somebody eventually realized, hey, wait a second. It would be a lot quicker if we had a shortcut to show 5. That's just my guess. The next system you see here is the Ionic Greek system. This system used the first Greek letters to represent numbers. So the first letter in the Greek alphabet is alpha, and the second is beta. That's where our word alphabet comes from, the Greek letters alpha and beta. And then we go on gamma, delta, epsilon, and those represent 1, 2, 3, 4, 5, and it keeps going. The problem with the Greek system is that they kind of ran out of letters because they needed different letters for each number as they went on and on and on. You're probably familiar with Roman numerals because we still use Roman numerals in certain sort of decorative instances. When I teach math for liberal arts, and some of you might be viewing this in that course, or most of you are viewing it in math for elementary teachers, I make sure that we cover Roman numerals because it's something that an educated person still today in North America should be able to work with. And as you know, the Roman numerals, the Romans also used letters. They used letters I, V, X, L, C, D, and M. And with those letters and with the use of a horizontal line above them for really large values, they could represent many different numbers. So they didn't have to worry about running out of letters like the Greeks did. So that was the Roman innovation, was that we're going to use groups of letters. So, for example, we have 1, when 2 ones is 2, 3 ones is 3. I'm going to skip this right now. We have 5. We have 5 plus 1, that's 6. 5 plus 2, that's 7. 5 plus 3, that's 8, and so on. The other sort of interesting thing the Romans did, so when we add things together like the Roman 6, 7, and 8, that's an additive system. So is the Mayan system. We have 5 plus 1, 5 plus 2, 5 plus 3, 5 plus 4, 5 plus 5. These are additive systems. The Romans also had a subtractive component. If a letter comes in front of another one, it is subtracted from it. That's because the Roman rule was that no more than 3 of the same letter could appear in a row. You couldn't have more than 3 I's, or more than 3 X's, or more than 3 C's, or more than 3 M's. 3 was the maximum. So if you wanted to show 4, you had to show 1 less than whatever 5 of that was. So 1 less than 5 ones, or 1 less than 10 ones. It's also a little more complicated because we could only subtract certain numbers or certain letters from others and stuff like that. Notice, I'll back up a little bit. I forgot to mention this. The other unique thing about the Mayans was that they invented a symbol for 0. 0 representing a place value. Represent there are no numbers in this place of the number. No numerals in this place, and what we represent the number as. The Babylonians eventually, if I remember, it was either the Babylonians or the Persians, also developed a symbol for 0 really near the end sort of their civilization's dominance at the time. It never really took off, and it was more of a 0 as in just to make sure you understood that there wasn't anything supposed to be there. It wasn't really part of place value. Historians of math have bitter disagreements of who invented the 0 first, and I'm not sure what your textbook says as they talk about it, but be aware that people don't agree. So if you read something that says, oh, this civilization invented 0 first, unless there is new information out there and they can prove that, it's still a matter of debate of if the Mayans came first or if the Hindus came first. Speaking of which, Hindu is today we think of Hindu as a religion, the Hindu religion. Hindu, the religion, comes from the ancient word used in Europe for India, which was Hind, Hind. And so Hindu here doesn't mean someone who is Hindu. It doesn't mean that religion as such. This means these are symbols that were invented by ancient Indians, ancient people in the Asian subcontinent of India. And it is either the Hindus or the Mayans who fight for credit of inventing the zero. In any event, the Mayan numbers did not spread. They, as far as we know, did not influence other native peoples in the Americas. They didn't spread at all. They remained with the Mayan culture. The Hindu numbers, on the other hand, did spread. And so whether the Hindus developed zero first or whether the Mayans developed zero first, it was the Hindu idea of zero that spread eventually across first Asia and then North Africa and Europe. And they spread because of Arabs. So Arabic, referring to the language of Arabs, the Arabs were traders throughout much of the Indian Ocean region. And they encountered, obviously, people living in India. They traded with them. And often numbers come from trade, because you need to keep track of how many things you have in stock, what you're selling, and stuff like that. And so they borrowed, or took, whatever you want to call it, the Hindu numbers, and they did some modifications for them, with them. And so you can see the Hindu symbols and the Arabic symbols aren't quite identical. And I should add, they also look a lot more, maybe like hand-drawn than these other symbols do. And that's unfortunate. The only reason they look like this is because we don't have, in type styles on computers, we don't have symbols that represent a Hindu number 4 or an Arabic number 4. We kind of do for an Arabic number 4, so I'm not sure why they're doing it this way. So they look almost like hand-drawn. Whereas, oh, look at how pristine the Greek letters look. Well, that's because we have Greek alphabets that are included in our numbers, in our fonts that we use for computers. When you look at the Hindu numbers, you can probably see lots of similarities with our number. Similarities for our number 0, our number 1, our number 2, our number 3. 4 and 5, a little harder to see similarities for. Our number 6, our number 8, our number 9. I should add that how these symbols look, again, they change over time, and they still change. If you have a student who comes to you from a different country and they already have gone to school, some of the way that they draw or they write some of their numbers, even though they use the same number system that we are using, might look different to you. And so a very common one, for example, that I sometimes see is a symbol like this for the number 1 that often I see from students who come from the Middle East, for example. So be aware that symbols do change. So the Arabic symbols, again, they came from the Hindu symbols, but we see some changes. Ours are a little closer to the Hindu than they are to the Arabic. But they came to European cultures through Arab traders. So that's why our current system that we use, and that is used through much of the world today, are called Hindu-Arabic numbers, or numerals. Numerals is the better term for us to use, especially in education. These, again, are not the only symbols. There's also there are traditional Chinese symbols, which are often also taught. They just don't happen to be in this particular chart. So there's many other ones out there as well. So a numeration system is a collection of symbols and properties that we use to represent numbers in a systematic way. In other words, it's not random. The first numeration systems were probably tally systems, and we still use tallies a lot, right? So we often do groups of 4, and then we do a sideways one to mark 5. Right? Someone who only knew the Mayan system would probably be able to pick up this tally system pretty quickly because it's kind of similar. Here's the full Egyptian system. And I should say that different books draw the symbols a little bit differently. But in general, we have symbols for 10. The Egyptians were also based around groups of 10, just as we use. So the Egyptian system would put a bunch of these in a row. So the Egyptian number 33 would have been this. It would have been 3 scrolls and then 3 staffs. 33. Or sorry, that would be sorry. The Egyptian number for 303 would be 3 scrolls and 3 staffs. 33 would be 3 heel bones and 3 staffs. Okay. My favorite Egyptian symbol is probably the astonished man for 1,000,000. Like, oh my goodness, that is so much. My second favorite symbol is the lotus flower, because in the textbook I use for Math for Liberal Arts, the lotus flower is drawn so that the actual flower part of it looks like a little Pac-Man, which it doesn't look like here. So the Egyptians only used symbols if that number were actually present, and they drew that symbol however many times there were. So 1,050,000 would be an astonished man, just one, because it's 1,000,000. And then 50,000 would be 5 pointing fingers. 1,050,000. Now, the problem with this system from our perspective is that it's really easy to write 1,000,000 here. It's just one symbol. But if I wanted to write 999,999, I would have to draw 9 pollywogs or tadpoles for 900,000, plus 9 pointing fingers for 90,000, plus 9 lotus flowers for 9,000, plus 9 scrolls for 900, plus 9 heel bones for 90, plus 9 staffs for 9. And so although the Egyptians could use these symbols to represent any number up to 9,999,999, and they may have had ways to represent bigger numbers too that we just don't teach, some of those numbers got really big. The Babylonians used just 2 symbols. They used downward pointing wedges and sideways pointing wedges. A downward pointing wedge meant 1, and a sideways pointing wedge meant 2. And these were grouped together in what we call a base that we'll talk about later in this video series. The Mayan system had these numbers, these 3 digits, and again, they were in different groups related to their base system. We mentioned already what the Roman letters were. Some examples of Roman numerals and our equivalents. And then our system that we use. We use the Hindu-Arabic numeration system or number system. All of our numerals are constructed from 10 digits. The digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The number 10 is not a digit, right? The number 10 is constructed from 2 separate digits, 1 and 0. We also use place value. In other words, this number is different than this number because it matters what place the number is in. The place value in our system is based on powers of 10. So we have groups of 10, groups of 1, and if we kept going, we'd have groups of 100, which is 10 squared, groups of 1,000, which is 10 cubed, groups of 10,000, which is 10 to the 4th, groups of 100,000, which is 10 to the 5th, and so on. our system is based on powers of 10. 10 to the 0 is 1. 10 to the first power is 10. 10 squared, or 10 to the second power, is 100, and so on. Different number systems used different bases. The Mayan system used basically base 20. It was a modified base 20. So they used mostly groups of 20. The Babylonian system used base 60. So they would go from up to 59, and then they would start working with, instead of groups of 1, groups of 60. And then they would get to 60 squared, which is 3,600, and they would have groups of 3,600. We still use base 60 today. Base 60 is used when we tell time. There are 60 seconds in a minute and 60 minutes in an hour. That's not something that is just part of the natural world. That is how we have chosen to tell time, chosen to measure time, and it is a direct descendant of how the Babylonian number system worked. The fact that there are 360 degrees in a circle, that's another artifact of the Babylonian number system. Now, we don't always use degrees anymore to measure circles, right? We also use radians in high school math and beyond. But when we use degrees, which is what we usually teach in elementary school, that comes to us from thousands of years ago and the Babylonian numeration system. So our system uses place value. Place value assigns a value to a digit depending on where it's placed in the numeral. So the digit 5, the value there is 5,000 because it's in the thousands place. If it were in the tens place, the value would be 50. If it were in the millions place, the value would be 5 million. Depending on the textbook, this place that you see here with the 8 is called, sometimes it's called the units place, and sometimes it's called the ones place. And something else we should know is that any number to the 0 power equals 1. So 10 to the 0 is 1. 10 to the first is 10, and so on. When we write a number in expanded form, what we're doing is we write the digit times the place value. So for 6,789, we would have 6 times 10 cubed, because it's in the thousands place, plus 7 times 10 squared, because it's in the hundreds place, plus 8 times 10 to the first, because it's in the tens place, plus, I would prefer this to be 10 to the 0, but we also see times 1, because 9 is in the ones or the units place. Now, in elementary school, when we teach expanded form, we usually don't teach it with exponents, because exponents aren't usually taught until middle school, or at least the upper elementary grades. So, but we still might teach something like 6 times 1,000 plus 7 times 100 plus 8 times 10 plus, and at the end, some places will just say plus 9, but it's better to be plus 9 times 1. Now, since you're in college, you should use exponents. But if you're ever teaching this, depending on the age of the students, you would write those out. So speaking of exponents, let's just review this. Exponents are a way of doing repeated multiplication. So if I write 2 times 2 times 2, that is the same as 2 to the third power. Excuse me, I'm losing my voice from talking too much on these videos. If I write 7 times 7 times 7 times 7, that is 7 to the fourth power. If I write 7 just by itself, we usually just write it like that. That's really 7 to the first power. We're only interested, so A here could be theoretically any number. Like it could be 1.4. and then n is going to be a natural number. And for our purposes, for up here, so from 1 to whatever. So 1.4 cubed would be 1.4 times 1.4 times 1.4. So using an exponent is a shortcut way of doing repeated multiplication. I'm going to leave it here for right now for this. There's a couple of other videos that there's at least one other video that we're going to talk about in this unit or in this section, but hopefully this helps you get an idea of some other numeration systems beyond the Hindu-Arabic system, as well as what expanded form looks like.